So today's lesson, it'll be the first one, and it's going to be focusing on and, or, and not statements. How does mathematical logic work with and, or, and not? So we'll start with and. Now you've seen and many times in the world, and you've probably said the word and many times, and so imagine this sentence. So to take this course, you need to have completed grade 10 math and be enrolled in a current course I teach. Or, the other statement, to be involved in Notre Dame graduation, you need to have 100 credits and completed 3 levels of religious studies. Now, if you just think about these two statements, there's kind of, I would actually say in each statement there are two parts to it. And more formally, we call each part a clause. So if we look at the first statement, you need to have completed grade 10 math is one part, and the other one is enrolled in a current course is the other part. Now, and implies that you need to be doing both of them for this statement to be true. So to be involved with Notre Dame's graduation, you have to have both 100 credits and also have completed 3 levels of religious studies. You can't have done one and not the other. Okay? So that's how ands work, is usually there's two parts, or again, more formally, clauses. And now you'll see, we'll learn later that each part can be more intricate than just a simple statement, but both have to be true. So now what we'll do is we'll see some symbols that we're going to be using throughout this mini course. The first one is when we're dealing with straight logic. It's kind of an upside down V. So it kind of looks like that. Because we're using a computer program to kind of learn through this, is 2 ampersand signs is what we're going to be using in the logic world in the program processing to represent and. Alright, let's deal with or statements. So let's look at the previous 2 statements, but this time instead of the word and in them is the word or. Now imagine I said, to take this course you need to have completed grade 10 math or be enrolled in a current course I teach. So this would imply if you're just simply in my photography class and maybe you haven't taken grade 10 math yet, that you would be allowed to take it. So not so bad. But imagine now our graduation policy was you have to have 100 credits or have completed 3 levels of religious studies. Now this changes the game drastically, because now a student could simply come to our school, have 3 classes of religious studies, and be able to graduate. A little silly, but if this was their graduation policy, they would logically be true and able to graduate. So you'll notice that how the ors work is usually with 2 statements, or you could have 3 or 4, multiple ors, is that it's just one or the other. Now in the logic world, we deal with what's called inclusive ors. Inclusive ors implies that you can actually have both. So if this was our current graduation policy, and a student completed 100 credits as well as 3 levels of religious studies, he or she would be able to graduate. The symbols we're going to use is the regular V, and in the processing world we use 2 vertical lines. Now the vertical line key is found above your enter key and below the delete button, and you have to hold shift to get there. Alright, now let's deal with nots. So how do nots work? Now nots are a little different because you don't need 2 statements to deal with a not. So imagine just this. To take this course you need to have not graduated. So all this is we would simply ask you that if you have graduated, meaning it is true that you've graduated, then you would not be able to take this course. Or to be involved in Notre Dame graduation, you need to not have less than 100 credits. Now you'll notice this actually is one of our parts of our current graduation policy, because the current graduation policy is saying that you have to have at least 100 credits. So to say you cannot have less than 100 is actually implying that you have more than or equal to 100 credits. So now nots, it depends on what you're dealing with. There's multiple ways to write nots. We have this, so this symbol. We also have a tilde, that sometimes is a not. The last one in processing is an exclamation mark. So what we want to do when we're programming, if we don't want something to be true, is we start it with an exclamation mark. Now, like I said before, you could actually have just one statement, and it could be not. However, we can actually do now nots of ands and ors. So imagine if we kind of put everything we've been talking about together. So let's say the common, obviously, phrase that you've heard multiple times and seen posters all around our school, that you're not allowed to drink and drive. And I hope you never do. So let's let A, so whenever I refer to A, that's going to be the event of drinking, and B be the event of driving. So if I was to put this in a very logical mathematical sentence, it would look like that. We would have not, and then in brackets A and B. So again, if you just kind of read that as a mathematical sentence, I would read it as not A and B. Now, knowing what A and B are, we could say it is not the case that you can drink and drive. So that's where they say math is the universal language, is that actually, as we start learning more about logic, that's an actual sentence, just those couple of symbols. So now what we're going to do is we're going to do what's called a truth table. So I want you to just take a look at this as I'm talking about it. A truth table starts on the left, and it puts on, so if you look at the first two columns, A and B, is those two columns, if you'll notice, each row has every single possibility that A and B could be. So the first row would be imagine if someone was drinking and driving. The second row would be the event that someone is drinking, but they're not driving. The third would be that they're not drinking, but they're driving. And the last one is they're not drinking and they're not driving. Okay, so let's look at the third column. So the third column is going to be just an and part. So the third column reading would be drinking and driving. So the first row, obviously, the person is drinking and driving. And for every other row, they are not. They are either not drinking or driving, or they're doing neither. Okay, so if you look at the fourth column, now this would be the case that who is not drinking and driving. So in the first scenario where it's true, true, that person is actually drinking and driving, and hence they're breaking the law. And this statement would be a false statement. But in every other case, they are either not drinking, they're not driving, or they're simply not drinking and they're not driving. Okay, the last column I wanted to show you is what we call an equivalent statement. So I want you to kind of take a look at that. And what has happened is reading that says not A or not B. Meaning, if I then replace A and B with drinking and driving, it would say not drinking or not driving. Now, if you actually think of that like kind of as an English sentence, that it should make sense that they are identical. If one poster said you're not allowed to drink and drive, and another poster said simply don't drink or don't drive, that actually is the equivalent sentence. How we prove that mathematically is show that they have equivalent or equal truth table values. Okay, let's look at the not of an or statement. So imagine your parents said to you, you're not allowed to go to Billy's or Jason's house. Now again, let's let A be the event of going to Billy's house and B be the event of going to Jason's house. What this would look like in a mathematical logical statement would be the not of an A or B. So you can't have A or B. Now again, looking at truth tables, the first and second columns are identical again, taking on all the possibilities that you could have. So A could be true, B could be true, A could be true while B is false, A is false while B is true, and A and B are both false. And again, kind of a middle step is let's see what happens with A or B. Now again, if you remember, we always assume that this is an inclusive or, and the or says one or the other or both. So the only time that the or statement would be false is if they were both false, which is the last row. Then taking the not of that statement, as seen before, is just simply flipping the trues to false and the falses to trues. So in the fourth column, you will see that this statement is only true if you did not go to Billy's and you did not go to Jason's. And you'll notice how I said that. How I said that is actually the last column. The only way it's true is if A is false and B is false. So you'll notice what happens when you take the not of an A or B, or take the not of an A and B, is actually the and switches to an or vice versa, and both statements become nots.